So when the children come in for neuroimaging, we start by sending out a storybook to the families, and the storybook has this question. You know, what is something that you use every day, but you've probably never seen, okay? And of course the answer is your brain. And so we try and get the children interested excited about coming in for the imaging, and most often it works quite successfully. They enjoy the experience and they have fun, and they get pictures of their brains, which they love to take and have show and tell with. So I'm going to show you a little bit of that. This is how we start, and then there's a whole storybook so they know who they're going to meet, where they're going to go, what they're going to do, so there aren't any big surprises, and that makes it easier for them. So our neuroimaging at Sick Kids, and the other thing I should say is that I'm presenting the data from Sick Kids because that's where I'm dealing with those data, and so I'm focused on Sick Kids, although there are other sites at McMaster and in London that are dealing with neuroimaging as well. So these are our two research pieces of imaging equipment. There's the MRI, it's a 3T, and the MEG, magnetoencephalography. And I'll give you a little bit more information about that later, but you've heard already today a number of discussions about the importance of EEG. Well, MEG is almost the same thing, but better. But it isn't possible in animal models, but it's a very nice way to look at brain function, whereas MRI allows us to look at structure as well as some measures of function. And they're both totally non-invasive. The neuroimaging that we've completed with POND, we do several types of MRI scans. We do 3 types of structural scans, functional scans, as well as MRS, which is looking at brain metabolites. And then in the magnetoencephalography, we do functional scans. It's only a functional system. And I wanted to just show you the numbers first. This is what Evdokia just mentioned. So the neuroimaging at Sick Kids for POND started in June 2012. So we've been doing this for almost 3 years now. And our total number, the purple, is this going to work? Where's my mouse? Nope, that's not working, okay. The total number is about 235 in total. This is a cumulative average. You can see that ASD, we have just over 100, and then the ADHD and OCD are around just below at 50 or just below. And this is what Evdokia mentioned as well. You know, ADHD has got several times the prevalence of ASD, but we're getting way fewer of them in the neuroimaging arm of POND, so we need more of them. And so the data that we've got the most of, that we're most sure about, is from the ASD, and so that's what I'll be showing to you today, but we just need more of the other groups. We're starting to analyze them now. So I'll show you a couple of examples in these few minutes that I have of measures that we're obtaining from the brain imaging, just to give you a flavor of the types of measures we're doing and hopefully get you a little bit excited. If your children haven't participated, then they'll be interested in coming in. So I'll show you some measures of gray matter, white matter, the metabolic measures I mentioned, and then some functional measures. So the measures of brain structure. This image shows you examples of measures where we can take the thickness of the cortex. So how thick the cortex is all over the brain. And this is a comparison between children with and without autism. And you can see the brain has lots of blues and reds, and the blue is where the children with autism have slightly thicker cortex, and the red is where the children who don't have autism have slightly thicker cortex. And you can see it's just a patchwork. And there are some areas that on the bottom left, you can see that there is the one area that's a bit thicker in children with autism, another area that's thinner in children with autism. And these are fairly variable. And so we get these patterns, but we don't yet have a reliable measure in cortical thickness between these groups. Okay, so we can get these nice measures, and we're hoping to use them in the future, but right now they are showing us that there's not a big difference between those two populations. Their brains are different, a little bit here, a little bit there, but they are very much more similar than different. We can also look at deep gray matter, and look at brain volumes of the deep gray matter. And this is the hippocampus. You can see it's a deep brain, the hippocampi, there are two of them, are deep brain structures, and they're related particularly to memory and learning. And you can see there that the children with autism have slightly smaller hippocampi than the control children. And the thalamus is another deep gray matter structure. It's in the center of the brain, and it's sort of like a way station for sensory processing. It's a big hub, if you will, in the brain. Again, it's slightly smaller in the children with autism. But if we looked at the cerebellum, the little brain, the back part of the brain, you can see it on the top slide in the side view. You can see it there very nicely. If we break it up into all its little component parts, there are a few of them that are bigger in children with autism, and they also show a different developmental trend. And so this is something that we're excited about. There's some areas, there's a lot of work to be done on the cerebellum. We don't understand its function and its role in the neurodevelopmental disorders. And so we're going to be focusing more on that as well. And I'll show you some other slides from the cerebellum. But again, we're getting little differences, but basically the brains are quite similar. We can also look at white matter, and this is with diffusion tensor imaging. You may have heard of it, but it looks at the way water moves in the brain. So you know our bodies are mostly water. I mean, we don't feel like water, but we're mostly water. And in the brain, we can look at how the water flows in the brain. So if you think of water flowing down a street after a big rainstorm, it will flow the direction of the street. It won't flow across the street, right? And so we are able to look at how it flows in the brain, and it shows us the white matter pathways or the information highways in the brain. And there have been studies showing that children with autism, other neurodevelopmental disorders, have atypical white matter. And so this was a subgroup of children that we've looked at, about 60 in each. And we can see big differences here in the DTI. This is a fractional anisotropy, so this measures the directionality of how those white matter tracks are. And you can see that all those areas in red are areas where the children with autism have like more immature white matter tracks. There's less fractional anisotropy, and this measure of the white matter development increases with age, and these children with autism have less advanced maturation, if you will. And these are not little tiny dots. These are big effects here. So we need to look at this in greater detail with our whole cohort, because now we have 100 and then 50 ADHD and almost 50 OCD children, and then we can correlate that with the behavioral measures. The third sort of almost structural measure that we're looking at, it's not really structure, but it's not function either, are the metabolites in the brain. And so you heard something about the synapses and brain function in the earlier talks this morning, but the neurotransmitters are really important, and we can measure those, but they're the harder to measure than some of the other groups. And you can see that we're looking at GABA and glutamate, and we're mainly looking at the cerebellum because it's an area that we can image. And so far, we've imaged more ADHD than the other two groups, hardly any OCD so far. But we're just starting, because this was the most challenging imaging to get going in children. We needed special sequences on the scanner. And you can also see what they look like. So where the arrows are pointing, you can see the middle one, the child with OCD, you can see a little double peak, like two little rabbit ears, where that arrow is showing, and it's a double peak, but you can see it's quite hard to see. And this is in the glutamate peak. And then the GABA response. Again, you can see that it's sort of this little bump. And so we're just starting to get good data. And then we can go in and quantify this, and people who understand MRS, not me, I'm much more in function, will be able to determine if there are differences in these brain metabolites and how they are different in the different neurodevelopmental disorders. So this is one we're just getting going on now. So I want to go into brain function. So we have these measures of brain structure, and they aren't, a lot of the measures aren't looking radically different. And we know that the brains look usually pretty normal. And so it must be function, or it's more likely, that's not quite fair. We are optimistic that we'll get good measures, maybe better measures with brain function to start with. So we're trying to look at brain function. So I'm going to show you an example. Again, this was done with children with autism, and it's a working memory task. And so this isn't one of the ones that we've run in Pond, but we've run it in parallel with Pond. And one of the reasons is, I don't know, if I go back to that, if you remember that big graph where I showed all the numbers going up, where we had 235 children, one of the very, very bottom ones, where we only have about 12, were control children. And so we're just started pulling control children in, and so we really need more controls, because in order to analyze our clinical groups, the neurodevelopmental groups, we need to know what typical children look like. And so this is an example of a memory task, and this is typical of what we try and do when we're doing this functional scanning with the children. We have tasks that are friendly, child-friendly images, and these little clowns, as you can see, are wearing all different colors. And it's a color matching task, and the children have to pay attention to the colors that the clowns are wearing. It doesn't matter if there's a red hat or two red mittens, it's still red. And they have to remember which colors they saw, and then they see another clown and whether that clown has the same colors. So it's quite a difficult task, and in the children that we've been running, we've ended up stopping at the 4th level of difficulty. Let me show you an example here. So this first little clown, they would see that clown, and they'd look at the colors, and then they would see the second one. The first one would go off the screen. They'd see the second one and be asked, is that the same color, or the same colors? Well, no, they're different colors, right? Because the first one, he's got yellow and red, and the second one, he's got yellow and orange. And then that clown would go, and they'd see another clown, and they're the same colors. Well, it's the same, because it's yellow and orange again, etc. And so it's a way, they're looking at the colors, but they're sort of a child-friendly task. And when we looked at this in children with autism compared to children typically developing children, we see very different brain networks. Now, both groups of children were able to do this task. A lot couldn't do the task, I must admit. We lost a lot. But we lost them in both the typically developing and children with autism. But the ones that were able to do it, their performance was about the same. And so they're able to do the task, but what they're activating in their brain was quite different. So you can see all the areas in red in the control children are areas that were activated more and more as the task got more and more difficult, as more and more colors were added in. And the blue areas are areas that are activated less as it gets more difficult. And that's, the children would downregulate some parts of the brain to put more energy into the parts that were important for the task. And you can see that the typically developing children use a lot of the frontal lobes, particularly the ACC, whereas the children with autism were able to do this task just using the visual lobes, it seemed, in terms of a coordinated function. So it is interesting to look at this and then try and figure out how they're using their brains differently to be able to do the task. And I mentioned the areas that are downregulated, and this shows an example. So you can see that some areas it's important to downregulate when they are trying to do a hard task. Some areas of the brain need to be shut down so they can concentrate on the task at hand. And you can see that certainly on the right-hand side in particular, the children with ASD start to do this and then kind of level off, whereas the control children keep down-regulating. So they're showing greater modulation with difficulty. So they're responding to difficulty. They're differently from the children with autism. So I'm going to end with a couple of examples in magnetoencephalography, because you've already heard today how important the timing is, how important EEG is, and MEG is the magnetic counterpart. And its advantages, the MEG, you saw that little scanner at the beginning, it's less intimidating for children, and it's totally silent. So it's totally silent, and they aren't totally inside a tube, so they find it easier. It provides exquisite temporal information like EEG, but it also gives us very good spatial information like fMRI. So we have the best of both worlds with MEG. I've already said that. And like fMRI, we can do a lot of different protocols on an MEG. We can do lots of different cognitive tasks, sensory tasks. There's a wide range of the type of information we can look at. So I'm going to start with an example from another working memory task. And this was, again, this was a much simpler task than the one with the clowns. And the children were shown these colored patterns one at a time, and they just had to respond if a pattern repeated. And this shows one that's called a one back, because it's the one before. So it's an immediate repeat. And so it looks really simple, but by the time they've seen over 300 of these colored patterns, they all start to look the same. So it really does, especially for young children, have some impact on their working memory. And you can see here, we get this nice localization with MEG. You can see that red dot there is the right hippocampus, which is involved in encoding recognition memory. And you can see on beside that there's a big, the big bump at around 0.4, so at 400 milliseconds or 0.4 seconds. That is where the typically developing children, they show greater activation in their hippocampus when they're recognizing stimuli compared to the flatter line where that's the new stimuli that aren't being repeated. Whereas the children with autism show that greater activation for both new and old stimuli, so they aren't differentiating between something they've seen before as well as something that they haven't seen before. And that activation is correlated with behavior, and I think this is where we want to go with neuroimaging. We want to get it related to behavior and to symptoms. You can see here, the black line shows you that the greater that activation, it would really be nice to have a pointer, the greater the activation, that bluish red at the top, the more the accuracy of the typically developing children, and it has no impact on the children with autism. But the children with autism were doing the task, and so they recruited the left insula. So at around the same time, you can see this big activation in the ASDs, the very bottom plot there, and that big peak that is significantly different when they recognize something. And there, it was correlated with their performance. So their reaction times got faster as their activity there got bigger. And it had no impact. The typically developing children weren't using that area at all for this task. So you can see that with the neuroimaging, we're able to see that the children with autism, they're doing the task, but they're using different parts of their brain to achieve success. And the other thing is that we can look at something like this activation in the anterior cingulate, a very important part of the brain for cognitive tasks, and their performance in typically developing children is much larger when they're doing the task. With children with autism, it wasn't really related in terms of their performance, but their activation there was definitely related to their symptomatology. And so we're able to find brain behavior correlates that are indexing individual variability. And this, I think, is a big step in the right direction to try and use neuroimaging to understand individual differences. The last task I'm going to show you is an aphasis protocol. I'll just show you 2 slides here because everybody is aware that emotional phases and face processing is one of the hallmark problems with children with autism, but it's also problematic with children with ADHD. They also are poor in recognizing emotions in particular. And so this has been done in about 100 children, and we're running adults now as well. So we're recruiting adults with autism now. And this shows you another example of the types of imaging results we can get. This shows you a network in the brain in MEG. And this network, it turns on at around 0. You can see the 0 timeline. And that big green activation is the strength in that network in the control children. And the blue line is the much lower strength in that network when the children with autism during the processing of angry faces. So this was for angry faces. There was no difference for happy faces. They were processing, these were adolescents, they were processing the happy faces similarly, but not the angry faces. And so they were able to see networks in the brain. We know that the right insula is part of the limbic system. It's very important for emotional processing. And so we're able to see how this is variable. And then this is something that we can do in the other children as well. So in POND, I believe we have this enormous opportunity to understand the brain-behavior relations in children with neurodevelopmental disorders. I've shown you examples from children with autism, but certainly we are now getting close to the numbers to analyze the others as well. The structural brain imaging shows some significant differences at the group level, but they're not pervasive and they're not strong enough yet to show us individual differences. And so we're moving, I'm really excited about the functional brain imaging to see how the brain function differs with the diagnosis, and it varies with the symptoms as well. And because of the sensitivity of these measures, certainly the functional measures, it has a huge potential to be using them to monitor interventions. And if you remember, again, on that graph I showed you with the cumulative numbers, we are using this with children who are undergoing interventions like pre and post interventions to see how interventions impact these measures of brain function. So I certainly want to acknowledge everybody who has been involved in this work, and our other centers that are also using, like the Master and Lawson, who are doing brain imaging as well, and we're all pulling together. Thank you.